developing next-generation research and technology, facilitating connections between AFRL industry and academia, unlocking innovation through a culture of collaboration. This is the AFRL Regional Network Midwest.
The main objective of our project is to establish the design of a morphing metastructure that is able to adopt two different shapes that are optimal for different flight regimes. To achieve these, the main outcomes that we will be delivering is a design tool that, through optimization, establishes the geometry of the metastructure that is needed to achieve two desired shapes for our vehicles, and a demonstrator that closely matches the design shapes that we obtain from this design tool. So in the last increment of this project, we focused on establishing the metastructural design that would provide us with the ability to switch between the two desired flight conditions. And we were successful in establishing this design tool based on finite element analysis and optimization to essentially obtain from the optimization process a distribution of dome-shaped units and their local shapes that allow us to morph from a desired target shape to a second desired target shape. So during this second increment, we have been improving our initial metastructural concept, and in particular we're focusing on reducing the amount of strains that the structure undergoes when morphing. So every time one of these domes changes shape, it undergoes a significant amount of strain that is small but still significant. So we perturb and change the local geometry to minimize these strain concentration, allowing us to use higher stiffness materials such as metals. So the process to obtain designs that reduce the amount of strain that the units undergo when being snapped requires the use of some mechanics of shells and combined with fabrication and finite element results. So our initial steps determine that by cutting out parts of the dome, we are able to reduce the amount of strains that the structure undergoes when snapping. Effectively, we're reducing the points of stress concentration that occur due to the inversion of the dome units. So our current results show that by introducing the cutouts in the domes, we have a significant design space for obtaining bistable units that is larger than what we had when we analyzed completely covered domes. And we also determined that if we allow for small amounts of plastic deformation to occur, the design space becomes much larger. In particular, this expanded design space allows us to find geometries that we could fabricate with additive manufacturing in metals, such as this dome here, that are sufficiently compliant to undergo a snapping cycle. So in these first initial steps, we still require some more design and results to obtain bistable metal domes, but we made significant strides, and we will continue this investigation to obtain bistable domes in the next few weeks. We have further conduct analyses on the effect of introducing this geometry that has reduced strains on the global capacity for morphing of these metastructures, and our results show that we are able to still retain the morphing capability, which provides us with a good path forward to simultaneously reduce the stresses that are needed for snapping these structures, which allows for using structural materials and still match the desired level of morphing that we want to have these optimal shapes for different flight regimes.
I'm Nathan Hertline.
I'm Phil Buskell. We're both from the Air Force Research Lab, and we're the sponsors on this Midwest Hub project, which is a novel combination of material science and mechanical design to address and explore challenges in morphing high-speed vehicles.
We're really excited about the AFRL Midwest Hub model, which encourages a unique teaming between academia, industry, and the lab.
And we've enjoyed the brainstorming and engagement with Professor Andres Arrieta's group, Professor Rodney Trice, as well as Canopy Solutions as part of this project. Looking forward to the outcomes.